Hi everyone, welcome to the fifth video in our series on sample size planning. This is part of the sample size planning workshop hosted by the North American Society for the Psychology of Sport and Physical Activity. And as always, these videos are meant to be kind of a complement to the activities that happened live in that workshop. But hopefully, if you're catching up on this later, or even if you weren't able to attend the workshop, there'll be some useful and interesting information for you. In this video, we're going to kind of continue what we've done in the previous videos with simulating different study designs using R. And basically running a series of mixed effects models under different conditions to see which results are statistically significant or not, and then estimate, the statistical power, assuming a certain alternative hypothesis is true. And the study that we're basing this on is this study by Daniel Cabral et al., published in the Psychology of Sport and Exercise, where they were looking at if learning a skill with the expectation of teaching versus the expectation of getting tested on it changes your performance of that skill under psychological pressure. So is it a low pressure test or a high pressure test? And as we talked about in the previous two videos, that's already a complicated design, right? We started with just simulating the difference between low and high pressure tests. Then we added the component of was it being training with the expectation of teaching or the expectation of testing. And now we're going to move into their full design, which is actually even more complicated because they were looking at that teaching versus testing on the low pressure test versus the high pressure test, but they also had this added factor of the method of instruction. Was someone being given analogical instructions, or were they being given very explicit declarative instructions about how to execute this golf putting skill? So this creates a 2 by 2 by 2 design with repeated measures on this last factor of post-test, and radial error in the golf putting task was their dependent variable. And if we look at their data on figure 1, you can see again that their design looked a little bit like this. So they had a pre-test where they assessed everyone's kind of baseline skill with golf putting. Participants trained under the different conditions for several blocks of practice over one day. And a handful of those blocks are shown here. And then a day later, participants came back for the low and the high pressure test. And you can see for each test, we have a group of participants who trained with the expectation of teaching, right? And a group of participants who trained with the expectation of getting tested. And then within each of those groups, right, half of them trained with analogical instructions and the other half trained with explicit instructions. So here we have that 2 by 2 by 2 design. And what we're going to do today is simulate pre-test data, the two post-tests, and then also simulate those data for each of these different groups. And fortunately, these authors very generously made their data publicly available on the Open Science Framework. So we can actually go download their data. And then what I did was create just a pivot table in Excel to look at some of the means that we're going to be using, right? So for our simulations, we're going to start with using the means that were found in this study. And we're gonna use this as our first simulation here. But as I've talked about in the past, this isn't actually exactly what you want to do for a power analysis, because we don't want to assume that Cabral et al. Found the true effect, right? It's very unlikely that they happened to observe the exact means in each of these groups in each of these conditions. So we'll start using the means and the standard deviations precisely from their study based on the data that they provided, and we'll look at the simulations that way. And then we're also going to be a little bit more conservative and maybe change some of these numbers and say, okay, well, what if this difference was actually a little smaller than what they found? What would the statistical power look like in that situation? And that's going to be really important because if you remember in our previous videos on statistical power concepts, we talked about post hoc power. And post hoc power is not a good way to do statistical power. And if we assume that exactly what Cabral et al. Found was correct and is the truth, that's a post hoc power calculation. And as we'll see, that's a self-fulfilling prophecy. When I simulate the population using exactly these means, it turns out they had 100% power to detect the three-way interaction they were interested in. if I use their data as informative, but change the actual means and become a little bit conservative, now I'm doing a priori power, right? And I'm saying, okay, well, what if reality looked like this? What's the smallest effect size we might be interested in? And if I do that, right, now I can actually run a series of simulations using different parameters that are not a self-fulfilling prophecy. And as we'll see, the statistical power for this three-way interaction is very contextual. And in this original study by Cabral et al., I also want to briefly come back up to look at the number of participants they ended up with, because they did do an a priori power calculation in their study, right, to get the sample size that they collected, and they included 148 participants. So with 4 groups, that works out to be about 37 participants per group. And that was based on some previous research and estimates of kind of a medium effect size they used a standardized effect size measure based on some previous work of the expecting to teach effect. So they did an a priori power analysis, estimating what they thought might be a reasonable effect size for the three-way interaction. They happened to find a statistically significant three-way interaction. So this first time through, we're going to simulate their data exactly, effectively doing a post hoc power calculation. And then the second time through, we're going to be a little bit more conservative and do an a priori power calculation that gets modified based on the data observed by Cabral et al. So in this script, right, so this is in the GitHub repository, which is linked in the video description. We're going to use these R packages to simulate populations of data the same way that we did before. And I'll talk through the first group, and then I'll kind of go quickly through some of the other groups, because this is something that we've done before. Now we're just doing it multiple times because we have more groups to deal with. But first I'm going to simulate a population for the expecting to teach analogy group. So I'll set the seed, I'll set the size of the population. I'm going to create a vector of means based on the means that we observed, from Cabral et al., right? So I can pull out the means for my expecting to teach analogy group. So those are these 3 means here. I just rounded them off to put them into my simulation. We have an estimated correlation matrix, and this is, again, an approximation based on the data from Cabral et al., but pre-test correlated at about 0.6 with the other post-tests, and the post-tests correlated a little more strongly with each other. So this is simplified, but this basically reflects that we had positive correlations and pretty strong positive correlations between tests. Next, we'll create a vector of standard deviations. Again, these are standard deviations in each group on the pre-test, the low pressure test, and the high pressure test, right? Collected or estimated from the data by Cabral et al. Then I'm going to convert that into a covariance matrix by doing a little bit of matrix multiplication between the correlation matrix and the standard deviations. I will then use the multivariate random normal function in order to simulate this population. So we'll call this teach distribution. It's going to be the size of the teach size argument, which was 1,000. It's going to have 3 columns, which have means based on the teach the teach mean vector, and those 3 columns will have standard deviations based on the covariance matrix. So you can see once I do that, here are my simulated individuals on a baseline, a low pressure test, and a high pressure test. And I'm going to rename these variables a little bit here to relabel this as the teach analogy distribution, right? Clarifying that this is for people who expected to teach, receiving analogical instructions, and this is my hypothetical, assumption about what the true distribution of people who learn a golf putting task while expecting to teach while receiving analogy instructions. So for each row, I'm just going to say that it's teach, and also that the method of instruction is analogy, and then I'm going to rename my columns to be pre-test for V1, low pressure for V2, and high pressure for V3. And if I do that, now we can also look at these data. And you can see now, okay, each person is a row. I've got my 3 different repeated measures here, and then which group they were in and the method of instruction for that group. In the subsequent 4 sections here, I'm going to do the exact same thing, again, using the means and the standard deviations from Cabral et al. To create a simulated population for people who expected to teach but had explicit instructions. and a simulated population for people who expected to be tested but had analogical instructions. And then a simulated population of people who expected to be tested but had explicit instructions. So again, these are all things we did before. So I went through that kind of quickly, but you can revisit the previous video if you have any questions about, exactly what's going on in the simulations of those different populations. And then finally, I'm also going to show, this is something that we've done before, but we're going to use a linear mixed model in order to get some p-values for our various main effects and interactions here. So what we'll do, is create random samples. And for this example, I'm just going to take samples of size 10. I'm going to bind those samples into one data frame, and then I'm going to pivot that data frame longer in order to get the data formatted the way I need it. So you can see here I've got a column for subject ID. I've got 2 observations per person. Their pretest score is a static variable because there's only one pretest value for each person, right? This was then someone who was expecting to be tested, had analogical instructions, and then I have 2 observations, one for the low pressure test and one for the high pressure test, and these are the simulated radial error scores for that participant on those 2 tests. So next, I'm actually going to create my mixed effect model. So again, because I have a repeated measure here of test, I'm going to have a random intercept for subject ID to account for the within subject nature of that test variable. And otherwise, this is a mixed effect model that would give you something equivalent to a factorial ANOVA. I'm going to be controlling for pretest, and then I want the fully factorial design of group, method, and test, all their main effects and all their interactions. And again, you wouldn't have to use a mixed effect model here. You could use, the AOV function, or you could use something like the easy ANOVA package. Any statistical, analysis that basically fits your question, you could simulate. I like to do this using a mixed model because mixed models are very flexible. If you wanted to add in things like missing data or some other potential constraints. So I just think the mixed model framework is a really useful way of going about this analysis. And this particular mixed model, is equivalent to a factorial ANOVA where we're controlling for pretest as a covariate. And if I do that, right, I create a model object called mod0, and then I could use, like the capital A ANOVA function, or I could use the little a ANOVA function. And you'll get like slightly different answers because the big A ANOVA uses a chi-squared test. The little a ANOVA, if you have the LMER test package installed, is going to give you an F value. And I like this approach because, again, if our goal is to kind of create an analogy to the factorial ANOVA, we're going to want F values with denominator degrees of freedom. So we can get those for each of our different observations, each of our different effects. And what we're most interested in really is this 3-way group by method by test interaction. And you can see in this sample that I took, that happens to be statistically significant. And as in the previous videos, if I want to pull out individual p-values, remember that these statistical outputs are lists, so we can use square brackets to access the particular values that we want. And I'm just showing you how we can index basically that final column, right? And then from that column, each of the rows that we want to get in order to ultimately pull out the p-value that we're most interested in, which is the p-value for that 3-way interaction. If you also wanted to, you could capture the descriptive statistics, in terms of the means and the standard deviations. But with these 3 groups, that's actually going to get really big. So, you could kind of embed something like this in your for loop in order to save the means and the standard deviations that you want. And you can see an example of where we did that in the previous video. But for this example, because we've got these 3 groups and it gets a little cumbersome, I'm just going to focus on statistical power and extracting the p-values from each of our samples. So now we get into the meat of the actual simulation, right, where we're going to create a vector of sample sizes that we're going to go from 30 up to 100 in steps of 10, and we're going to do 200 iterations at each sample size. And again, if you were doing this on your own, you might want to think about exactly the range that you want to test at and then the number of iterations you want to run. And in general, you're probably going to want to do more like 500 or 1,000 would be a lot of iterations. The more iterations you do at each sample size, the slower this for loop is going to run, but the better your estimate of statistical power is going to be. So kind of a good place to start if you're doing this on your own is to test a smaller number of sample sizes and a smaller number of iterations. Make sure it kind of runs. And then once you get the range of sample sizes you think you might be interested in, you can really increase the number of iterations in order to get precise estimates. For illustrative purposes today, I'm going to go from 30 to 100 because 30 is a pretty good starting point for any between subjects design. You're seldom going to want fewer than 30 people per cell. And we'll go up to 100, and I'll just do 200 because that's kind of enough that it'll probably be reasonably accurate, but small enough that it'll also run a little bit faster. And as per the previous videos, we'll create a blank data frame where we're going to save the results of our simulations. This one's going to have a lot more columns now because I have a lot more p-values to save. Once I have this 2 by 2 by 2 design, now there's a lot more interactions that I actually need to account for. Oh, whoops, I forgot to create my n's and my k. Okay, perfect. And now I can actually create my simulated data. All right, so I'm going to initialize row equal to 0. I'm going to set seed equal to 1. And then I'm going to go ahead and let this for loop run the exact same way as before. The only difference is that now, right, we're taking additional samples because we have 4 different groups. So there are 4 different populations that we have to sample from. But otherwise, this is exactly what we did in the previous video where we were looking at the interaction between expecting to teach and whether it was a low pressure test or a high pressure test. Now we have the added wrinkle of the method of instruction, so we have to have both a test analogy and a test explicit, a teach analogy and a teach explicit, and then when I model those things together, I have to have the fully factorial group by method by test design. I'm going to control for pretest, and then I'm going to save all of those p-values as we go through my for loop. And this is going to run 1,600 times because I'm going from samples of size 30 to size 100 in steps of 10. And I'm doing 200 observations at each sample size. So you can see I have my counter here to kind of indicate our progress on the screen. And this will take a moment to run because, you know, it's got to do all 4 of those samples. It has to run the model, and then it has to save the p-value each time. And then it has to do that 1,600 times. So again, this is why you have to be a little bit careful about how many simulations you want to run versus how long you want to sit around at your computer. And because we're doing this for illustrative purposes, you know, I've kind of limited the number of iterations so that we can actually get to the results a little bit faster. Okay, so once that's run, now we have, you know, our full list of simulations. So you can see that at every sample size, we've got a different simulated experiment, right? That's the iteration. Then we have the p-value for the covariate, the group main effect, the method main effect, the test main effect, and then our various, you know, group by method, group by test, method by test, and finally the group by method by test interaction. And to estimate statistical power, right, what we're ultimately interested in is assuming that those kind of means that we plugged in at the beginning and the standard deviations we plugged at the beginning are true. That is, assuming that a real effect exists, what is the probability that we're going to get a statistically significant result? So we can do that now simply by summing the number of p-values that are statistically significant, assuming that we set alpha at 0.05, you know, and we're not correcting for any multiple comparisons or anything like that, right? But we can just sum to find which effects are statistically significant. And then that creates a pretty large you know, table still. So it's going to be really helpful to actually plot that, because if we look at even our summary statistics from these simulations, right, you can see, all right, at every sample size, you know, we've got the effect and we've got power. That's a lot to handle visually. So let's actually turn that into some plots. And in this case, right, I'm going to create a faceted plot where I'm showing you each effect as its own panel and each curve showing you statistical power. It's a little hard to see here, so let me go ahead and actually save this, and then we will open this up from the current directory. And you can see it a little more easily here. Basically, we have, you know, the covariate is always statistically significant. The main effective group, right, starts out pretty low at sample sizes less than about 40. And even as we get up to sample sizes of about 100, it's almost impossible to have, you know, we don't have 80% statistical power for that group main effect. The main effect of method of instruction, however, right, is it explicit versus analogical instruction, seems a bit stronger, right, with that actually maximizing pretty early on at about 60 people per group. And you can kind of follow these curves for everything. But the main thing I want to show you here is that this group by method by test result, which again was the main hypothesis of the study by Cabral et al., and was statistically significant in the study by Cabral et al. If we now use that one study as our estimate of statistical power for the interaction, we have great statistical power as soon as, even at a sample size slightly smaller than what they used, which was about 37 people per group. And this is the problem with post hoc power. If we assume that what Cabral et al. Found was perfectly the truth, then a power calculation just becomes a self-fulfilling prophecy. It's just redoing your statistical significance test. If you had an effect that was statistically significant, like this three-way interaction, guess what? Post hoc power will tell you you had the power to detect it. If you had an effect that was not statistically significant, like this group by method of instruction interaction, post hoc power will say, hey, you had no power to detect that because it happened to be what you observed in your sample. So again, this is why you wouldn't want to use exactly the numbers that you saw in a published paper, and you wouldn't want to click like the post hoc power button in SPSS, because post hoc power just doesn't make sense. It's based on a bad assumption that what we observed was exactly the truth. It was perfectly accurate. So what do we do instead? Well, let's come back to our simulations. I'm going to clear our workspace here just to make this a little bit neater. And let's come all the way back up to the top. And actually, let me pull up the descriptive stats from Cabral et al. Again. So let's really focus especially on what's happening in our expecting to teach group, because that's where they really thought that the effects of analogical instruction would make a difference. They had previously observed that when participants expected to teach, they did worse on a high pressure test compared to a low pressure test. And that was this explicit analogy group here. So this is what they had kind of historically studied, and they had generally found that error got worse on the high pressure test compared to the low pressure test. They added in the analogical instruction group because they thought that this might be a remedy to choking under pressure, and then if you had analogical instructions, maybe you wouldn't choke as bad. In their study, they actually saw a crossover interaction where not actually analogical instructions led to you doing better under high pressure, right? They had a mean of 46 compared to a mean of 54. And then explicit instruction led to a significant, a very substantial amount of choking. They're doing about 20 centimeters worse on this test. So what we might try to do then is say, okay, well, what if that general pattern is true? We think that this three-way interaction is real, but we don't think it's as strong as it happened to be in the study by Cabral et al. So we're going to be a little bit more conservative. So let's rewrite this and say, okay, rather than 54 to 46, let's assume that analogical instruction just keeps your performance stable. You're not going to get better from low pressure to high pressure. So we'll come back to our simulations here. Let's make that like 54 and 54. Okay, and then let's look at the explicit group. Now here we saw that their performance went from a 47, right, up to a 65. So let's assume that maybe this choking under pressure effect is real for the explicit group, but maybe it's not quite as big as this. So let's actually take their mean maybe up to the same place and say that they also had a 54 here, and then we'll maybe take this down to like a 60. So we'll go to my explicit group, and we'll say that this was a 54 to 60. So now the general pattern is in agreement, right? We're still predicting that three-way interaction, but we don't think the effect is as strong because Cabral et al. Happened to find that analogical instruction actually led to improved performance on the high pressure test. And now we don't think that's true. We just think your performance will be stable, right? So it's 54 to 54. And then similarly for the explicit group, Cabral et al. Found that these people did almost 20 centimeters worse. And we said, okay, well, I think they'll do worse, but I don't think they'll do that much worse. Maybe Cabral et al., happened to get a big difference with their small sample size. Because one of the things that we know is that if you have an underpowered study, when you have a statistically significant result, you often get an exaggerated estimate of the real effect. This is something referred to as the winner's curse in statistics, right? Because p-values reward extremeness. In an underpowered study, you tend to overestimate the real effect. So let's assume that, yes, choking under pressure is real in this group, but maybe it's a difference of, 6 centimeters rather than 20 centimeters. And so now let's rerun our simulations the exact same way, but we're being a little bit more conservative with what we think is actually going to happen in our expecting to teach group when they're receiving analogical instructions and when they're receiving explicit instructions. We'll keep our expecting to test groups the same for now. And then let's recreate all 4 of those populations. And then we'll redo our power calculation. And again, we'll stick with 200 iterations at each sample size. We'll repeatedly sample from all 4 of those populations. We'll fit the linear mixed effect model, and we'll get a p-value for every main effect and interaction. And then we're going to add all those up to get the statistical significance in each of the in each iteration. Okay, so after that runs, we've now, kind of created a new version of reality in which to sample from, right? And that version of reality thinks that the results of Cabral et al. Are mostly true, but may have been an overestimate, right? So we basically just downscaled the choking under pressure effect, and we also equalized what was happening in that expecting to teach analogy group so that they were at least not choking under pressure, but they weren't actually getting better under pressure, as Cabral et al. Had observed. So now, having simulated that new reality, right, we can create the same statistical summary that we had before. We can generate a new set of plots. And let me actually go ahead and save this output. And now we can compare our 2 sets of results side by side. So here is our first one. And here is our second one. And you can see if we kind of go effect by effect, there are some pretty important differences here, right? Our covariate always remains statistically significant, right? That's not too interesting. Your pre-test is related to your post-test. People who are good at putting remain good at putting in both versions of reality, right? And you could kind of go effect by effect here to see the ones that are most interesting to you, but let's specifically focus on this 3-way interaction, right? Cabral et al., if we accepted their descriptive statistics as exactly correct, and that is the true effect of this 3-way interaction, that's post hoc power, right? And we had this amazing outlook. We were like, yes, we only need 37 people per group, maybe a little bit less. And you know what? We can actually observe that effect with great regularity. By tinkering with those results, right, and actually saying, well, what if there just simply was no improvement under pressure for the expecting to teach group? For the under analogical instruction, what if there was no improvement under pressure? And what if when there was explicit instruction, they just didn't choke as bad? Admittedly, we made it quite a bit smaller, but we essentially wipe out our ability to detect that 3-way interaction. And now we're only using 200 iterations at each sample size, but even granted that these might not be great estimates, you can see we're not really seeing any ability to detect a 3-way interaction here, because now we've made the effect of method on testing more similar between our 2 groups. So we've essentially gone from accepting that there's quite a strong version of this interaction as found by Cabral et al. To saying, well, what if there's a much smaller, almost trivial version of this interaction, right? And you could see that basically wipes out the statistical power that we might have had. So now the question becomes, right, well, what actually is the truth? And this is where we don't actually know. It's safe to assume that the results from Cabral et al. Are probably an overestimate, given that it's the first demonstration of this effect and looking at kind of the history of science, right? Oftentimes effect sizes get smaller over time. So it's reasonable to accept that the interaction is probably somewhat smaller than what Cabral et al. Found. Maybe we were a little too overly skeptical, right, in our simulations, and we really wiped this effect out. So maybe the truth actually lies somewhere more in the middle. And that's where actually simulating a range of different possible alternate realities is really powerful, because now you could go simulate a few different conditions, right? Look at the sample size you need under each of those sets of assumptions, and then have an informed discussion with your team about what you think is most plausible and what sample size kind of satisfies those results the best, right? Because then you have this kind of compromise between here's what we think is happening in reality, here's what we can reasonably collect. Where do we fall across a bunch of different possible power simulations? And then you can have a very informed perspective on the sample size you need when designing your study.